Thank you, everyone, for joining me today. My name is Dr. K, and I'm going to be going over a slightly more technical introduction to Quai Network. So to start, we need to first understand the limitations of monolithic blockchains, and more specifically, the physical limitations of monolithic blockchains. When we think about blockchains, what we need to first wrap our minds around is that inconsistency at consensus causes delays, and it causes inefficiency in the work function. So if I'm a Bitcoin miner and a Bitcoin block comes in, and I have every single one of the transactions in that block, and I've pre-computed, well, I can't necessarily pre-compute, but I know those transactions are valid. All I have to do when somebody propagates the header is I have to reconstruct the root, and I have to say, does this make a valid state transition? So I have all the data when the header comes in. Great. All I'm limited by is my computation time and my disk hits. That's very, very fast. What happens if I'm missing 10% of the transactions that were included in that block? So I'm now inconsistent at the time that consensus took place. Does anybody know? I have to go through my network of peers and hope that I can find that set of transactions before I can continue to commit and process transactions doing useful work. That is delay. And the worst delay in these systems are the network delays. Because they're supposed to be decentralized systems. They're supposed to have many nodes distributed across the globe. So many nodes we'll call N, and the distribution across the globe is a ping time. So if I'm all across the globe, I can have ping times of 100 milliseconds. And if I have 10,000 nodes like a Bitcoin network with 10 peers, I'm going to have to make 7 hops around that network to be able to make one trip. And if I'm collecting stuff, I don't know how many trips I'm going to have to look for to collect that information. So that can lead to significant delays post-consensus, right? And what happens if what can I do at that point? I can potentially continue processing stale state. I could, in the case of Bitcoin, start processing empty state. But in both cases, I'm kind of wasting work that's going into the network, and I'm increasing my likelihood of getting an uncle or an orphan block, Bitcoin terminology, right? So what are the things that drive up that property? I kind of already hit on the first one, which is number of nodes. If I have one node, can I ever be inconsistent? If I have 2 nodes, I can be inconsistent, but I can probably quickly resolve that inconsistency. And as I keep going up in the number of nodes, I keep increasing the ping times, and I keep increasing the number of hops. So if I increase nodes, I'm increasing my inconsistency, holding everything else constant. So why would I not have transactions?
Miner chooses to mine transactions before a broadcast.
That's one reason. Or we know that there is a propagation delay of transactions within the network. So if I have a lot of transactions that are getting generated all over the network all the time, the more that happens, the more likely I'm not to have yet received a transaction just based off the fact that there's a latency to propagation when that block is found. So if I increase the number of transactions, I'm also going to increase the likelihood that I'm missing data and I'm inconsistent at the time that I find a block, right? The other thing that will increase is block speed. So the more often I force this thing on the network, the more often this is going to happen. So the faster I have blocks, the more time and the more chances I have to be inconsistent. So in a first generation blockchain, there are delays between consensus and consistency, and they're exacerbated by these factors. And they ultimately limit throughput. So how do we address these? What can we change to address these issues and minimize delays? So for each one of those items that I previously mentioned, the increasing number of nodes, one thing that I can do is I can create a subnet. And I can shard the data that each one of those subnets is responsible for. In terms of transaction throughput, I can create scope of transactions, which leads to creating subnets and shards And then I also can create pre-aggregated or pre-committed sets of transactions that propagate as sets rather than individual transactions. In terms of block speed, what I can do is I can have different block speeds. Some fast block speeds so that I get liveliness, and some slow block speeds so I'm more likely to stay consistent in different contexts. And that again leads to subnetting and shards. So subnet and shards can decrease delays. Do people get that first part before I keep going? That was good? Sweet. Okay, so subnet, shards, and sets are challenging. And what challenges do they present? So when we look at shards, we need to be able to shard state without sharding work. Okay, so it's perfectly fine for us to have two different data sets. But when we talk about the original purpose of a cryptocurrency and the fact that we're making an economic commitment to a set of data, there seems to be an implicit incompatibility with being able to shard committed sets but not shard the commitment. Right? Does everyone get that, or should I go into that a little bit more? Okay. So when we're mining a Bitcoin block, what we're doing is we have a header, and a miner is looking for a nonce. And that nonce is just a random number. And when they do a SHA-256 hash of the header plus that nonce, they end up getting a result. And the way Bitcoin works, and most cryptos work, is they say, I have a difficulty target. The difficulty target is the measure of how hard that problem was to solve. And that problem is how many leading zeros do I have in the resultant hash from the header and the nonce. So mining is looking for a nonce that creates a header with leading zeros. So if I'm saying I'm having two data sets, and that is a singular function that can be applied to a singular set of data, but I say I have two data sets, that would imply I can either choose to mine this set of data or I can choose to mine that set of data. That creates a challenge. Because if I do that, I'm splitting my network hash rate, I'm splitting my economic consensus into those two data sets. So that's a challenge. The other challenge is how do we get the shards to reference each other in a trustless way? This gets into the problem of bridging. If we look at loosely coupled systems, there's never a guarantee in a loosely coupled system that you ever can get disparate context finalization. So let's talk about finalization. How long does it take a transaction in Bitcoin to be finalized? Simple answer that most people would go with is that it's 3 blocks or it's 6 blocks. The real answer is that it never is finalized. It only logarithmically approaches a value of 1, and that's economic finalization. Meaning, if I have an economic incentive to attack a transaction, I can do so. So the amount of the transaction that I'm actually trying to make dictates how long it takes to be finalized, given the amount of economic input is going to the commitments. I'll give an example. If I'm at 7-Eleven and I'm buying a Coke for $5, and I do a Bitcoin transaction, the clerk looks at it, there's 1 block. 1 Bitcoin block is worth $150,000 in mining rewards. They're going to look at that and they're say, well, you could hypothetically be running an eclipse attack, but your benefit of doing so would cost you X and you would get Y. Meaning, you'd be able to walk off with your $5 soda and you could reverse that transaction on it by creating an eclipse in the blockchain, but the cost of doing that would be at least $150,000. Potentially much, much more. So as the clerk at 7-Eleven, if I have 1 Bitcoin block and you're buying a $5 soda, great. On your way, sir. What if I'm in exchange and you just deposited $50 million? When do I get finalization?
When $50 million worth of block rewards have been emitted?
Approximately, it's the cost of the attack and the rollback. But roughly speaking, if we don't want to get into time and the geometrics, just call it linear. And that is the right answer. So that means, depending on the size of the transaction, 1 block could be enough, or you could have to wait 500 blocks or 5,000 blocks, depending on the size of what you're transacting and your need for certainty and finality. So when we look at 2 different contexts, and I'm talking about 2 different blockchains, Ethereum, proof of work Ethereum and Bitcoin, and I want to go cross-chain, I never fully understand that either one of those contexts has actually sent in a finalized way. I'm making a statistical guess. Right? Because if I send money from Bitcoin to Ethereum, and then something happens that causes a rollback in Bitcoin, right? That wraps Bitcoin or whatever it is that I'm crossing chains with, it got reversed in one context, but didn't necessarily get reversed in the other. And the fact that these are loosely coupled, I never get a guarantee of finalization. So I would have to wait infinitely long to have certainty that I'll never get a rollback. Now I can statistically say, well, for this economic size, I can wait this long, but that obviously gives a very slow level of liveliness and finalization in cross-chain transactions. And more importantly, if you ever do get a rollback, there's no recourse to reset. So just because Bitcoin has a rollback doesn't mean Ethereum's going to go and be like, wait a second, guys. Bitcoin just rolled back and we're loosely coupled. We're also going to need to roll back. No, it's going to just keep humming because it has a different consensus. Loosely coupled systems. So one of the difficulties with sharding is when you have loosely coupled shards, they're hard to trustlessly reference. Another challenge of sharding. And then the other one that's related to that is synchronization. How do I guarantee that as a shard goes forward, that if something happens, the shard also goes back with its sort of coordinate or sibling sets? Another challenge to sharding. Okay, so then creating sets. So if we have transactions and we want those transactions to propagate more efficiently in the network, and we would like to know something about how old they are so we can enforce delays to inclusion, we need to first put them into a set, right? And then as we have more transactions, we can more efficiently propagate them and we can push up our throughput. But who creates the set? And whoever that set creator is and propagator is now a point of centralization and is a point of censorship. So creating sets is a difficult problem. And then subnetting. So one of the things we can do, we said we had 10,000 nodes, and if I subnet those nodes, I can create a more performant network. If I divide it into 3 pieces with 3,000 in each one of those networks would be more performant, right? But how do I, in a decentralized way, subdivide the 10,000 nodes? It's also a challenge. The interesting thing of all these very esoteric and very challenging problems is they can be solved with a single thing. Merge mining. So what is merge mining, and what does it mean to merge mine a blockchain? Before I go, anyone have a question on that last slide?
Can you go back real quick? So for shards, sets, and subnets, are those tied to zone, region, or can they occur in any other places?
So, for the purpose of this slide, I'm just generically talking about shards. To answer your question specifically to Quai, every one of the contexts or blockchains within the braid is a shard. So a region is a shard, a zone is a shard, prime is a shard.
Do I remember correctly you saying the term sibling set? And if so, what do you mean by that?
So if I have shards which are trying to cooperate together, I could say call those a sibling. But at some point I need to coordinate them, right? So if you're looking at 2 zones in a region in that particular context, I would call those siblings. But if, take a different context, if you say, the proposal for proof of stake Ethereum, as it currently exists with a beacon chain and whatever, each one of those 1,000 proposed chains would be siblings. Okay, so merge mining. Who knows what merge mining is? A lot of people. Maybe. Okay, let's go through merge mining. So, merge mining, interestingly, solves all of those problems. And one of the obvious ones that it first solves is the question of how do I shard data without sharding work? And the way that I do that is I create a merge mined header, which is committing to multiple sets of data, potentially committing to multiple sets of data at once and referencing different contexts, right? So when I set the problem up, I said, you can choose to mine this context or I can choose to mine that context. What we do with Quai is we put the two headers together and you get to mine both. And then each of the context respects the fact that the other context may have data that is effectively superfluous and invalid or extraneous for their context, but is included in the header. So to them, it effectively functions as an extended nonce. Everyone get that part? Cool. Okay. Yeah, so some data is valid depending on the difficulty met. So for this example of a header, when I'm mining Quai, I have to pick what's called a slice to mine in. So I simultaneously have to, should have reversed order on these slides, but I simultaneously have to pick prime, region, and zone. I get to pick it, but I have to mine all of them simultaneously. And I have to generate one of these merge mine headers. So the headers have a pending header from zone, region, and prime. Now each one of those contexts has a different difficulty target. So zone will have a lower difficulty than region, which will have a lower difficulty in prime. And when I find a nonce, I can compare it to those things to figure out what type of block I have. So if I meet a low difficulty threshold, or the lowest difficulty threshold, I would get a zone block. And the data highlighted here would be valid in the zone context. If I meet the next difficulty threshold, I would find a region block. But when I find a region block, I've also necessarily met the zone difficulty. So I would also find a zone block. And then, if I find the highest difficulty target, I'll find a prime block, but I'll also simultaneously find a region and a zone block. So a miner can mine a slice, but in the process of mining the slice, they're looking for blocks in all three contexts in their slice at once.
You're talking about slices. Have you already defined what a slice is, or did I miss that?
I gave a brief. I should have reversed the two slides. So let me kind of give a summary, and feel free to ask questions on these points as I go through them. So we have the hierarchy. And in the hierarchy, we have a prime blockchain. We have, in this example, 3 region blockchains, and then each one of those regions has 3 zones. So each one of the blockchains has independent state. So they can progress independently of the others and make their own transitions without having to reference the others. And then what we have is something called a coincident block. So in that previous slide, I was talking about merge mining. And if I find a prime block, right, I said you also found a region and zone block. That is what we would call a prime coincident block. And what that has done is that has created a hash-linked reference that is now traceable in both prime, region, and zone in which that block was found. So now zone has a deterministic referenceable understanding of everything that has been referenced in prime prior to that point. So if I originated a cross-chain transaction from one context into my zone, that point at which I see that coincident prime block gives me a hash-linked reference back to it. The other properties, so those coincidence blocks provide eventual referencing. So this is the delay in global consensus. We will eventually always reference each other, but it will take time, and that is the trade-off we were making for throughput. It's fully composable and interoperable, so I can interact from one context, one chain to another chain, both from a value standpoint and from a smart contract standpoint. There's a single shared token and monetary policy across all the chains in the hierarchy. The difficulty is the highest in prime and in the lowest in zone. That means zone blocks are generated more frequently than prime blocks. Initially, we're setting target times of zone to 10-second blocks, region to 100-second blocks, and prime to 1,000-second blocks. We may be able to squeeze those numbers down, depending on performance. Maybe we can get them to 7 multiples rather than 10 multiples, which would enhance our global consensus and liveliness. Yeah, and the other key point here is because every miner is required to mine a slice, which includes prime, a region of their choice, and a zone of their choice, all work that is applied to any context is always applied to prime. And that's how you get sharding of state without having to shard work. Any questions on this slide? We're good? Sweet. Okay, so let's talk about the eventual referencing. So I mentioned coincident blocks, and a coincident block is a block that is valid in more than one context. It creates a hash-linked reference between the chains, and there are stochastic phenomena. So I can't say that every 30 zone blocks I'll find a region block. I can say on average, every 30 zone blocks I'll find a region block. Now that is a normal distribution, so some of the times I could wait 50 zone blocks. I could wait 100 zone blocks. It's just a stochastic process. I will eventually find that region block. I will eventually create the hash link, but it's stochastic, not deterministic. And that hash link reference between chains is the mechanism for transferring state across the chains. So the cool part is we've created a tightly coupled system that doesn't require anything more than Nakamoto consensus to coordinate or eventually coordinate all of the chains in the braid. Right? The work itself to advance any one of the contexts is the same work that creates the link between contexts. The other key point here is that these are independent chains. So if I look at progression, and I'm in Cypress 2, and I'm mining Cypress 2, you see that I just highlighted the next block in Cypress 2. So Cypress 2 is independently progressing. Cypress 2 finds a region coincident block at this point in time, and now all of that data prior to that block is now referenceable in Cypress 2. Cypress 2 keeps going. Eventually, it finds a prime coincident block, and everything that it can link back to, that's now highlighted, is referenceable from that point on in Cypress 2. So the chains can progress asynchronously and independently and eventually reference each other. The subordinate blocks don't need the dominant state, and the dominant blocks don't need the subordinate state. And the only time that we have to force synchronization is when we find a coincident block. And that is actually the limitation to how tightly we can change the mean block time in the hierarchical contexts. So the reason I can't say, oh, I have a zone and every block is 10 seconds and a region block is every 10 seconds and a prime block is every 10 seconds is because every time I find a coincident block, I'm forcing synchronization in that slice. So to make it so that my networks have better performance in the lower chains, I must have a difference in block times. So this is what we construct is called a braid. So with a braid, I was kind of showing you how things become referenceable in Cypress 2. And everything that's referenceable prior, there's 2 points. One point, something exists, but I can't yet see it. And another point is something exists and I can see it. So by the time everybody can see everything that's already happened, or it can be referenced, is what we call the finalization horizon. Anything that's prior to that, we call the fray. And the reason we call it the fray is because these tips are competitively advancing with each other. We don't really know who's going to end up as the leader, and there might be like roll forwards and roll backs in this context. And then once we go past the finalization horizon, we call it the braid. So the braid is the position which everybody everywhere can see, and is much less likely to have a reorganization. Okay, so the question that comes up is, in this setting, what types of nodes can we run? Why do we want to run them? And how can we use those to participate in the network? So we look at that hierarchy and we look at that structure. You're saying, okay, we have 13 blockchains, so the requirement is I have to run 13 different instances of Quai for all 13 different contexts. And the answer is you can do that, but the de minimis set that you have to run to be able to successfully mine is what we call a slice, which is the picking one, mining in prime, region, and zone. So you have to run 3 of the 13 nodes. Now, one of the interesting consequences of having that self-selected subnet for miners using a slice is that it causes the miners to want to topologically self-organize. If I'm a miner, I want to minimize the latency of data propagation to me from the network. So if I'm allowed to pick the set of peers which I have, aka what region and what zone I am in, I would like to pick the set of peers which have the lowest latency to myself. Because if I can minimize my network latency, I can directly impact the profitability as a miner by proportionally decreasing the number of uncle blocks that I mine. So what's a really cool property here is if we look at Bitcoin miners and Bitcoin nodes nodes don't even get paid in Bitcoin, funny enough. So Bitcoin miners, their incentive isn't to minimize, there isn't a strong incentive for them to do anything about network latency and trying to group. Because 1, there's no subnet to group into, and 2, given sort of the propagation limits of Bitcoin and the throughput limits, there isn't that strong of an incentive or likelihood to get uncle blocks. So they have basically no incentive to figure out how to get the network to operate in a more efficient and less latent way. But if you create this topology where people get to pick their slice, they will then self-organize into an optimal set, and they will achieve the greatest efficiency and lowest latencies possible as constrained by the wires and the routers and the internet.
So going back to last semester at Quai 101, we were talking a bit about the trade-offs in data availability, partition tolerance, and the trade-off space there, with consensus as well. I want to expand more on the data availability and kind of hear from you how this might compare to other blockchain solutions. So if we look at Ethereum and how they attempt to scale, they're using layer 2s, and they talk frequently about data availability. And the problem with data availability is that there is a kind of dilemma there called the fisherman's dilemma, in which we don't know if data is available to be proved on the base layer for a L2. And looking at how Quai does its sharding topology, having sort of lower subnets, as we're learning in Quai 102, how can we incentivize, or how does the network properly incentivize these fishermen, or these people running nodes, to ensure that that data is available and is properly validated and correct in these subnets or shards?
Great question. So I didn't really want to go into this in 102, but we can dive into it briefly. What ends up happening is, as a miner, if I only mine a slice and one of my coordinate zones ends up including an invalid reference, I will eventually find out about that fact, because there's going to be some number of fishermen that will also be either running a full node or mining multiple contexts that will identify that and cause a split in hash. So I'm somewhat dependent on other people to identify state transitions that I'm not monitoring as being invalid, or to choose forks that may be taking place, which I'm not aware of. And that's fine, because when they give me the block, they're making an economic commitment. And so my confidence in that commitment is not 0, just because they spent money on it. And as more blocks get built upon that commitment, my confidence keeps going up. The problem is I will eventually find out about this, but in the meantime, I could be mining a lot of blocks that get wasted. So I have an economic incentive, if that type of thing is happening in the network, to monitor, say, coordinate zones. So your immediately adjacent zone. So if I monitor my 2 immediately adjacent zones, then I won't have to wait to find out about reorganizations in those contexts or potentially bad state transitions. I will immediately know about them, so I will immediately be able to make a choice of which tip I should be mining and which blocks I should be uncling. If I don't do that, I'm going to have to wait till I can detect it by the hash rate in the network, which will cause me to waste more work than if I were to monitor that state.
So to sort of steel man that argument of monitoring the zones adjacent to you, what is that gray area to say, instead of I'm just going to run a slice and watch what I have versus running a full node and watching the whole network?
It's a trade-off in costs, right? So if you are just running one GPU, your hash versus your infrastructural overhead to run a slice is in a certain ratio. But if you have 1,000 GPUs, you have a lot more hash rate. So every second that you're wrong, you're losing a lot more money, which means you're probably willing to invest in greater nodes, in greater context monitoring to ensure that your hash rate is getting used efficiently. So that's really the trade-off. Also, I would point out, in the longer term, there are ways that you could construct things where you could do proving on top of just work, so that people could validate things out of context without having to transmit the entirety of the data.
So if I were to run in many contexts, would I necessarily need my miners there? Or would I just want to have nodes in those different contexts?
You will want to pick where you mine based off of the hash rate distribution in the network, such that you maximize your return by minimizing your latency and thus minimizing your uncle rate, while simultaneously picking the zone or slice which has the highest number of Quai per hash reward.
At some point, will Quai offer visuals on the number of miners on the network to be able to see where the opportunities exist?
Yes. So there's a stats page that we're working on. And we're also planning to add a feature to the mining software to give a recommendation to the user on what is most optimal by measuring ping times amongst peers as well as Quai per block. This is actually a very complicated thing, and it's great questions. I only did one slide on this because there's only so much you can fit in like the 102 presentation. The other thing that we have to look at is the complexity of how do we pick ahead. And one of the things that Quai introduces is what we call the hierarchical longest chain rule, or HLCR for short. When we're looking at how the hash rolls up, in terms of how likely I'm going to find a zone block versus a region block versus a prime block, and how that hash sort of is additive in the hierarchy, most of the time you will always find dominant blocks that have higher total difficulty than their subordinate blocks. So we can see this dominant. So when I say dominant and subordinate, prime is dominant to region, which would be subordinate to prime, and zone is subordinate to region, which would be dominant to zone. So what the hierarchical longest chain rule is, we basically pick the chain which has the greatest total difficulty, but we do it in the order of hierarchy. So I first must pick the longest chain in prime, and then I can pick the longest chain in region, which extends the longest chain in prime, and then I can pick the longest chain in zone, which extends that longest chain in region. And that is HLCR. Now, one of the interesting consequences of HLCR is some of the time I will actually lower my subordinate difficulty when a coincident prime is found, Normally, my prime or my dominant will always have higher TDs, but because it's a stochastic process, there will be situations where your subordinate actually gains higher TD than your dominant, like 3% of the time. And in that case, that subordinate TD must be set back to the dominant at the point of coincidence. Is every target difficulty from Genesis added up to that point in time? Any questions here?
Which difficulty is attributed to a block? How do you attribute a difficulty to a block?
Right. So if you go past the zone target difficulty, that target difficulty is added to your total difficulty to establish your new total difficulty. If you found a region block, you would add that difficulty in. Well, actually, so if I found a region block, so a coincident region block in zone, I don't actually do any adding. I just do setting. So I just immediately set my zone to my region's total difficulty. So there can be jump forwards, and some of the times there can be jump backs. It would just mean that you found a lot of zone blocks quite quickly between the region blocks. So your zone total difficulty advanced faster. Because on average, I would find a zone block every 10 seconds. But if I get lucky, maybe I find it in a second, maybe I find it in 2 seconds, then I get lucky again and I find one in another 2 seconds, another 2 seconds, another 2 seconds, bam, I just found my next region block. I could have outrun my region block by finding 9 consecutive zone blocks prior to region blocks getting found. So if I just consecutively get lucky, when that next coincident region is found, it would actually have a lower TD than my zone. But when I have a dominant block that's coincident, I always just set the subordinate to the TD in the DOM.
So this isn't necessarily on the note of HLCR, but more in regard to the architecture of the chain itself. How did we arrive on 3 vertical layers and 3 horizontal in each layer?
You're just asking the 3x3?
Yeah, was it arbitrary? Was it because we know that Namecoin started out sharing hash security with Bitcoin as a 1-to-1, so 2 chains. So how did it arrive on 3 versus 4 or 5 or whatever other number?
Yeah, no, good question. So there's 2 parts to this. One of the questions that should be asked is why are there 3 levels? And that's actually really important because if I have a hierarchy which expands too quickly, my liveliness is really bad. And so then my time to sort of getting even marginally better finalization becomes really long. So if you took sort of Ethereum's whatever their thing, where they have their beacon chain and then all these different shard chains. So they do 1 in 1,000, let's say, right? And this is proof of stake. So this isn't really comparable because proof of stake doesn't work. But the thing is, when they're doing that, how often, if you have to do a 1-to-1 linking reference, how often can you reference those 1,000 shards? It's 1 in 1,000 of sort of your beacon, right? So if it's too wide, I get no greater assurances of finality for a very long time. But if I do 3 levels, if I'm in a zone and I have this region, that region block's hitting me every 10 zone blocks. Great, right? I'm still waiting 900 for prime, but I'm not waiting for the first sort of acceleration of finalization for that long. So by having that intermediate layer, you get better liveliness, better finalization guarantees faster, and you arguably also get better Sybil resistance in this case, right? Because by having that hierarchy, it means that I should have 1/3 of the hash rate kind of monitoring the set of zones under that region, which means when I'm trying to say do an Eclipse attack or a Sybil attack or create a improper state transition in one of those zones, I have to really be attacking the region to do it. But if I had this very wide hierarchy, say I had 10 zones under 1 prime, it means I'd really be attacking 10% of the network, not 30% of the network. In terms of the 3x3 to start out, that's just kind of our plan for what we think is a reasonable start to what we need to provide in terms of TPS into the market before reorganizations start taking place.
I see. So if we run into any throughput capacity issues, there could be another layer added below.
No, hypothetically, you could do that. I don't think there's good arguments for creating more than 3 levels, but if we run into throughput, we'll go wider. So you'd end up with like 3 regions and 4 zones in each region. It would be like your next bump up, and then it would bump up again to 5 and bump up to 6. It would just keep going wider, and then eventually the regions would bump out, so then you get 4 regions instead of 3. Cool. The other interesting implication that this has is on network security. This actually took a long time for even me to realize. So we know that security, i.e. immutability, is economic. And we've discussed the fact that finalization occurs when an eclipse isn't viable, economically viable. We also know the block reward is proportional to hash. So what that does is this is kind of like from a given context, say the purview of a transaction getting processed in the chain, sort of how finalized it is, which is related to the total difficulty that it's achieved after it's been played. What ends up happening is in the zone, you're getting economic finality, but you're only getting it at the rate of zone block rewards. So if I'm paying $100 every zone block for mining, I'm only sort of achieving economic finality of $100 per block, so to speak. But what ends up happening, because of how we're doing the TDs, once I hit a region, right, that region block is going to be 3x the zone block. So now I'm going at 300 a block, right? The other thing that happens is we set that total difficulty. And the reason that we can do the setting is because now if I were to try to go roll back that zone transaction, I would have to roll through a region. So my ability to eclipse attack is no longer my ability to eclipse attack a zone. It's my ability to eclipse attack a region. So it's perfectly valid to then set that TD to the region TD at the point of coincidence. And then when I eventually get to prime, again, my finalization rate changes. Now I'll be doing, say, $900 a block. And if I were to try to attack that zone transaction, I would now need to roll back through prime, which is 100% of the network hash rate. The important point here, and the thing that took some time to figure out, is that the coincident causes a sub to inherit the DOM TD entirely. So we have different progressions of finalization, but once we get referenced in prime, we are as good as prime. So inter-prime, all the hash rate is committing to that transaction. And if I want to roll it back, I got to fight all the hash rate to do it, even if that transaction only exists in a zone. Any questions there?
But security is economic. That means that, like, if it's too expensive for me to do an attack, I won't do it.
Correct. That's how these work. And if somebody tells you they work any other way, they don't know how it works. I mean, I don't know how far we want to go down that rabbit hole. That's a whole other presentation, but like that is proof of work versus proof of stake. So inter-prime finality has the whole network's hash security.
And when do you hit inter-prime?
Once you have a prime coincident block. One of the other interesting things that has become emergent is once we have broken through the trilemma and created a tetralemma, we actually see a new dominant set of constraints emerge, which we can roughly refer to as network bandwidth. And with network bandwidth, there are effectively 3 things that we're trading off as we're trying to progress in compute state. We have the network latency piece that causes delays that we've talked about, right? So we've tried to optimize those by creating subnets, which create fewer hops, and by incentivizing those subnets to optimize in a way that minimizes ping latencies. We haven't talked about computation. So depending on the type of transaction and how much compute power I need to do to validate a state transition, that can take time and delays within the network. So if I have a very simple transaction, which is a simple UTXO, I just sort of validate two fields, plus, minus, whatever, and check a signature and apply it, like that's relatively inexpensive. If I do something more expensive, like validate a ZK snark, or do like a ring sig verification, or do a bulletproof, those things become orders of magnitude more expensive, and those can start to play in the latency of the network advancing. So instead of being able to like look at all transactions and validate a block in 10 milliseconds, it could turn into hundreds or thousands of milliseconds. So that's also a trade-off. The other thing that you're trading is your storage bandwidth or input-output operations on disk. Those are also a physically limited time constraint. And so the more I have to read disk or the more that I have to write disk, that's also a limitation for us. And that's driven by how many transactions I'm doing and how much state size I have. And these three things trading off, the interesting point is they're all measured in milliseconds. Right? In the inverse of milliseconds, if I put a numerator on it and I call it bytes, I get bytes per second. And that's bandwidth. So what we're really doing in our new constraint is the network bandwidth. And the network bandwidth is defined by how much network, physical transmission bandwidth I have. It's defined by how much computation I have. And it's defined by the speed of the storage mediums in the computers running the network. So like now we've arrived at like a real limitation. And you know it's a real limitation because I can put a physical quantity on it. And those physical quantities exist in all points of the triangle. So we can do a lot, but we're still limited by physics. And we're still doing a trade-off between throughput and global finalization. But I believe that the architecture that's proposed defines the physically limited frontier of what you can do with a blockchain. So these are the trade-offs. You come up with any other system, you're going to bump into the same trade-offs. Conclusions. A decentralized system can be built to handle all of human commerce. Merge mining solves issues associated with sharding and security. And the trade-off for throughput is delaying global consensus. Questions?
So if you go back to the security slide a bit, I had a question regarding the transfer of state. Can this transfer be done through, say, a dominant block of yours being included in a dominant block that's not necessarily your own zone? So I guess a better way of phrasing it is, if a zone block is included in a region, and that region is included in a prime by a coordinate zone, does my zone data still transfer through prime? Or do I need to be included directly in prime for my data to transfer? Ergo, can I like piggyback on someone else's prime block?
You only need to have a hash linked reference. So the second you become linked, you become referenceable.
I guess in this slide, then, looking at Cypress 1's second region block.
This one. The Cypress is second region block.
Yeah, Cypress is third block.
Cypress 1?
Yeah, no, Cypress, the region.
Oh, Cypress, okay.
The third block in Cypress.
Okay.
That block can piggyback off the fourth block in Cypress, for Cypress 1. Correct. Cypress 1 can piggyback through Cypress 2's prime block.
To C prime. Yes. Yeah. So as long as there's a link to another link, you can follow links. That's fine.
So you don't have to necessarily be included in the prime to get prime finalization.
Correct.
I know you talked about the means by which the blockchain achieves consensus. and this is a hotly debated topic, so maybe just like a couple of sentences on why Nakamoto consensus versus proof of anything else.
Great. I'll go on a tangent, and I will talk about tribes. The interesting thing, and what we're really trying to solve, is a problem that humans have been trying to solve since tribes. And the issue is, how do we coordinate? How do we coordinate efficiently, and how do we coordinate efficiently at scale? So in a tribe, you can have about 200 people, and your brain can roughly do a heuristic and know the contributions of the 200 people that you're loosely cooperating with. Great. Once we go past 200, we can't track it anymore. Either because we can't cognitively handle it, we don't have the time to interact with it and track it, whatever. So what we do is we create hierarchies. So we say, okay, well, now we're in a group of 2,000, but we only can track 200. So every 200 of us, we're going to elect one leader, and then the leaders are going to get delegated authority, and we're going to create a hierarchy. And in that hierarchy, what we want and how we are represented is social and it's political, right? You extend that concept, you get the federal government. Just take time, take process, federal government. The federal government is the result of us not being able to coordinate without delegation. The thing that's amazing about what blockchain has done, specifically proof of work blockchain, it is the first system that allows us to objectively coordinate at scale. So we were subjectively and politically coordinating at scale. Now we are objectively coordinating at scale. What do I mean by that? We agree to a set of rules. The set of rules are deterministic in code. They have mathematics that we can verify. I can't verify that someone's adequately representing me or they're acting in my best interest. All very subjective. Who's the best person to delegate authority to? Super subjective. You keep adding layers to that, you get massive inefficiency and poor outcomes. Right? So the fact that we have this system now that's global, that 8 billion people can participate in, we've invented the basis of a new language that is objective for humans to use to coordinate at a global scale. Right? So I said it's like a value transfer thing, but this is as fundamental as language. And the first thing that we have done is created the first syllable. But as humans, that is what blockchain is. Because now that we can objectively coordinate, now that we can transfer value in this verifiable and trusted way, every other system can then be built using that basis. So we don't need to delegate. We don't need to be political. We can coordinate based off mathematics, which is amazing. But the people that do and promote proof of stake don't realize what we just achieved. They say, oh, that's fine. Everyone just put their money up or, become part of this certified crowd that only the crowd lets in. Delegation. And then we'll vote on the outcome. Don't worry about it. We won't get corrupt. OFAC censorship. Change in supply. Change in monetary policy. Change in mining staking rewards. Right? So that's what people fundamentally don't understand. But what this is as impactful as language. But that only happens if you maintain objectivity.
Okay, so if you have all hash linked references to every block and every state change in Prime, does that mean that if I'm running a node of only Prime, that I could theoretically validate the state of the entire blade from just having the Prime state hash?
You have economic proving of validity of state outside of your context, you will also get a pre-propagation prior to that consensus point taking place of external transactions which apply to your context from the other contexts. So you only have to have information that is required of you, and the work by everybody else that does have that information is the mechanism. Short of doing a proving mechanism wherein you have certainty in alternate state. So like, you shouldn't be holding or validating other state unless you have the economic incentive to do so as a miner. But even if you do that, you should be doing it in a way which minimizes network latencies and then coordinating it in your own little overlay setting.
So you mentioned that blockchain is this kind of coordination tech. Do you think that it's better at coordinating some things and less good at coordinating others? Like you mentioned that some things may be subjective.
Yeah, anywhere you need money. No, I mean, I don't need money everywhere. I can coordinate my household without money, right? You know, I can coordinate certain things that don't have like economic impact or whatever it is, like without money, right? Like we can go play a pickup basketball game. I don't need money. They call each other and they're like, hey man, wanna play some ball? Coordinated, didn't need money for it. But anywhere you need money, you need blockchain.
Got it. So it's like financial in essence.
Well, it has to do with like economics and trust, right? The thing that you're trying to achieve with money is trustless transfers in a common unit, right? The hilarious part of that is, though, because we have debt-based money, it is completely socialized risk debt, right? So even if you have $1 and you have a physical dollar in your physical pocket, the actions of Chase Manhattan and how they choose to originate loans and the risks on those loans, if they were ever to have a systemic problem, creates immediate indirect risk to the physical piece of paper and the value of that physical piece of paper in your pocket. So because we have debt-based money, we inherently have socialized risk on every node that exists both ethereally and physically, right? But you don't get that with blockchain. As long as you don't create debt-based money on a blockchain. But yeah.
I've got a specific coincident block question. So when you find a coincident block, like let's say a region coincident block, you're only finding one nonce, correct? So you're not, are you actually finding two blocks, or are you finding like one big block that kind of encompasses the region and the zone data that you would have been finding?
Like visually,
Yeah. So
two blocks.
So there's only one nonce, right? So if we go back through this slide, I only get to find one nonce here. So all of these things that I'm proposing are like valid and deterministic from the data I have in my slice, right? What I get to permute to do my mining is the nonce. Now, if I meet the difficulty threshold of zone, I have a zone block. This other data here is superfluous to me. It's just extra data. As far as I'm concerned in a zone context, that's an extended nonce. Just a big nonce. But if I meet the region difficulty in my context as a region block, this is the important data to me. And the other pieces of data are nonce. Now, I've also found a zone block, which is meaningless to me in that region context, but it shares the same hash, right? So now both the region and the zone have a block with identical hashes.
How does it share the same hash if the data wasn't
Because I have
included
one
in finding the nonce?
No, the data is the same.
Oh, right, because it's included in the header.
Right, and there's only one nonce. So they have a shared hash now. So when I go back to do hash link tracing, I've pinned these two things together. Right? So then when I go from my zone and I say, what was my parent zone block? It'll say, oh, that was a coincident region block with this hash. And then I can go to the region of my slice and be like, okay, that's referenced. Like, give me all the data that I needed that's pertinent to me prior to this coincident block, and we can do it.
Okay, so like the region block in that case would technically replace, I guess, what would have been just a zone block if the difficulty was lower.
There's two blocks. There's a region block and there's a zone block. It's two blocks. Yeah. They just have the same hash.
All I'm asking is that, assuming we're adding new chains, we're kind of assuming that the network is loaded evenly with transaction data, with miners and such. So what happens when we see a larger concentration in, say, a region over the other two regions? And how does the network deal with that imbalance or react to that imbalance?
Right, so there's negative feedback mechanisms to imbalance, which is, as a miner, if there's more hash in one context, my reward per hash would go down. So I should figure out how to leave that context and mine somewhere else because it would be more profitable. So the miners in the incentive to maximize their revenue are incentivized to evenly spread the hash. Because only at the point where my reward per hash is equivalent in all places will I not move.
So covering the miner aspect, how does that feedback loop work for users? It's obviously largely correlated to mining, but
the user piece is tricky, and there's like a whole presentation on that. But generally speaking, what's happening is the throughput or the gas limit that's allowed in one zone is a calculation based off of the total demand in all zones. So if people are hoarding, or what's the word, favoring or coalescing in one place, it's going to cause them to be pushing up and past the gas limit, which is going to cause fees to rise precipitously, which would then give them a high incentive to figure out how to operate elsewhere. Cool. Barbecue.